Hello everyone. In the earlier class, we have seen design of buck boost converter and then its implementation on PSIM software. Okay. In today's class, we will see design of Sepic converter. Okay, and then its implementation in the PSIM. Okay, its implementation in the PSIM. So, why the Sepic converter is required? As I told you in the buck boost converter, whenever we have input range, okay, input range or input voltage range is around, let's take from 15 to 25. Okay, input voltage is around 15 to 25, and then we need an output voltage which is across around 20 volt. So in that case, we need a DC to DC converter which can which can be used either for a step down, it is like for the buck converter, okay, or it can be work as a step up converter, that is called as boost converter. So in this case, or in this scenario, or in this case studies, we can see that the input is 15 volt, 25 volt and output voltage is 20 volt. So we can use this we can use this. So 15, so it acts as an, it acts as a boost converter. Okay, in this case it is boost converter, or you can say step up converter. Okay, so it is you can say increasing the voltage from 15 to 20 volt, and if it is for 25 volt, okay, it acts as an converter or step down converter. Okay, so we need a special type of converter. Okay, likewise buck boost converter we have already seen. This is what uh, uh, this is what which comes under the one of the topology. So other than buck boost converter, we have a cuck converter, then flyback converter, which will work on the same principle. Okay, which will work on the same principle, or you can say it will act as an buck boost converter, or it will act as an step up or step down converter at the same time. Okay. So this converter, like you can say a cuck converter, and then flyback converter, and then we have seen uh, buck boost converter, boost converter, and then this one is Sepic converter. So all these converter are nothing but single ended primary inductance converter, single ended primary inductance converter. Okay, all these are classified as. So what are the advantages of this buck boost, or you can say sorry, Sepic converter over this buck boost converter? So in the buck boost converter, we have seen that the uh, uh, output is inverting. Okay, output is inverting. So whereas in this case the output is non-inverting. Okay, so the output is non-inverting. Okay, output is non-inverting. Let us take a design problem. Okay, so taken one problem. Okay, so like we have so the parameters which are there, like given we have Vs, that is source voltage, is around 9 volt. Okay, and then what is given is that the output voltage V0 is 6 volt. Okay, and then change in the L1. Okay, change in the inductor current. Okay, L1. Okay, I will rewrite this. Okay, I sorry, it's given at L1 is equals to change in the inductor current across L2 will be 0.4. It has been given, and then change in the voltage across capacitor 1 is equals to change in the voltage across capacitor 2, that is equals to 0.1. Okay, and then frequency has been given is 100,000 hertz. Okay, so it's 1 lakh hertz. Okay, it's 1 lakh hertz. Okay, this is what is has been given. So if you, now we need to design a Sepic converter. So I will draw the diagram here first. Okay, so we have this first inductor. Okay, one inductor is there here, supply voltage is there. Okay, and then inductor is connected to the switch. Okay, so if we use MOSFET, so drain will be connected to this portion. Okay, so this is my switch, and then across switch we have, again, sorry, across switch, so when inductor is connected to the capacitor, now in this case here. Okay, and then it will connect the second inductor, okay, that is your L2 in this case. This is L1, this is C1, okay, this is bypass capacitor, and this is L2. Then the diode is required, and then another capacitance, that is C2, and we have a resistance across it, load resistance, and we will take an output voltage across this, that is our V out, and this will be our Vs, or you can say V in. Okay, Vs or V in. So we need to design, we need to find out the value of L, we need to find out value of C, okay, L1 C1 and L2 C2, and then it has been given, that is uh, power has been given, okay, power, or you can say load has been given, that is 12 watt. So we need to convert, we need to make, we need to find out the value of resistance. Okay, if you know the power, we can find out the value of resistance. Okay, we'll see one by one. First we will find out, as we have seen in the earlier converters. Okay, so we'll see, find out the duty ratio, find out the duty ratio. Okay, so we know that how to find out the duty ratio. So duty ratio is calculated. Okay, so it is, I will write down the formula. So V0 or V out is equals to V out plus Vs. Okay, we'll put this value in the calculator, and then we'll get the value of D. Okay, so what is the value of D? So just wait for a minute. Okay, we know the value of VO. Okay, we know the value of VO, that is, in this case the 6 volt is there, V out voltage, and then Vs is 9 volt. We'll calculate this on the calculator. Okay, just hold. So it is enclosed. So 6 divided by 6 plus 9, and that value is 0.4. Okay, that value is 0.4. So duty ratio we got 0.4, and then percentage is nothing but 40%, you can say. Duty ratio 0.4 and the percentage is 0.4%. So sorry, percentage is 40%. Okay, so this 40% we need, actually we need for PWM when we use the switch over here. Okay, for PWM pulse we'll have to make a calculation. So so you know that for 100%, okay, we have 360 degree, and then for 40% how much? So we can calculate the uh, 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 we can calculate this. Okay, so 360 multiplied by 40 divided by 100, that we can calculate, of course. Okay, and that will comes out to be 360 multiplied by 40, and this will divided by 100, it will be around 144. Okay, so it will be around 144. So whenever we give PWM pulse, so we have to give PWM pulse at 0 144. Okay, so we need to understand this. Okay, 0 to 144. Next we will calculate the average inductance current. Okay, first we will calculate average inductance current for L1 and L2. Okay, so average inductance current, it's recording. Average inductance current IL1 we will calculate. What is the value? IL1, it is nothing but what is the power has been given, Vs divided by your Vs. So it's around 12 by 9. Okay, So 12 by 9 we can calculate it around 1.33 ampere. 12 by 9. Okay, so it's 1.33 ampere. You can say 1.3 also. Okay, 1.3. And then so this is what the second step. The third step, we have to calculate the average inductance current across L2. Okay, so it's like IL2, which is again nothing but PS. So it's IL2 is across, you can say, output resistance. So we'll calculate PS divided by VO. So it's around 12 divided by 6. So it's 2 ampere. Okay, so it's 2 ampere. Next, we need to find out the value of maximum inductors current. Okay, so IL max we need to find out. IL max we will find out. IL max. So IL max, okay, that is again in the inductor 1. So IL1 max. Okay, I will calculate IL1 max. So it's equals to IL1 plus delta change in IL1 divided by. Okay. So we know that IL1 value is 1.33. So it's 1.33 plus change in IL1 that has been given in the problem, that is 0.4, and then divided by 2, which we will calculate. So 0.4 divided by 2, so 0.2 plus 1.33. It will be around 1.53 ampere. Okay, so it will be around 1.53 ampere. And then we'll find out IL minimum. Okay, so maximum we have find out, that is 1.53 ampere. IL minimum can be calculated as IL1 minus delta IL1 divided by 2, and this IL1 value we have this 1.33 plus change in the IL1, that is change in the current, that is we have this value 0.4 divided by 2. Okay, so 0.2, this value will be 0.2 plus 1.33, so it will be like uh, sorry, it is I have made a mistake. Okay, 1.33 minus 0.2, so its value is 1.13 ampere. Okay, 1.13 ampere. We will find out the maximum current which is flowing through the inductance L2. Okay, so that will be the I think this will be the 5 step, this will be the 6 step. Okay, so IL2, and that is maximum. Again the same formula, IL2 plus delta I2. Okay, delta I2 divided by 2. Okay, so we know that the value of IL2 is 2 plus 0.2 divided by 2. So this is like 0.4. Okay, 0.4, so 2.2. Okay, so 2.2 ampere. This will be the value of your IL2 max. Okay, again we will find out the value of IL2 minimum. Okay, so IL2 minimum value we can find out. So it is nothing but IL2 minus delta I2 divided by 2. So 2 minus 0.4 divided by 2, so it's around 1.8 ampere. Okay, so this is what IL1, IL2 maximum and minimum we have find out. Okay, and where it is used in the calculations of inductance. Okay, it will use in the calculations of inductance. So we'll calculate first now L1 value. So what is L1? So L1 can be calculated as Vs into D. Okay, that is your duty ratio multiplied by your switching frequency Fs, and then delta L1. Okay, delta IL1. Okay, so we know that Vs value is 9 multiplied by D value is 0.4, duty ratio value is 0.4, and then we have Fs which is 1 lakhs. Okay, 2, 3, 4, 5 multiplied by 0.4. Okay, and we'll calculate this value. So 9 multiplied by 0.4 delete divided by zero 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 multiplied by 0.4, bracket complete. So it will be around 9.9 9 into 10 to the power minus 5. Okay, 9 into 10 to the power minus 5, or you can directly say it as 90 micro Henry. 90 micro Henry. This is what the value of L1. So we can calculate the value of L2 again with the same formula, only the change in the in this term. Okay, so VSD divided by Fs into delta IL2. Okay, so VSD, we know that 9 into 0.4 is there, and then Fs value. Okay, Fs value. Yes, so value of delta IL1 and delta IL2 is the same. You can see that. Okay, both the value are same. So we'll get the same value here also. Okay, delta IL2. Okay, so 1 lakh multiplied by 0.4. So both the terms are same. Okay, so we'll get 90 micro Henry here in this case. Okay, 90 micro Henry. Now the next step is we need to calculate the value of capacitance. Okay, so in order to calculate value of capacitance, okay, so we'll calculate the C value of C1, that is when V out multiplied by D into R. Okay, here we need to calculate R, and then F S, and change in the voltage across the capacitor 1. Okay, so what is this value? So we need to calculate the value of R first. Okay, so R, we have power has been given. Okay, so value of R can be calculated as V out square divided by P, okay, PS, or you can say power. Okay, so it will be like we have, this is 6 square. Okay, V out is 6 square, and then power has been given 12. So it's 36 divided by 12. So it is like 3 ohm. So R we got is 3 ohm. Okay, L we got 90 microhamp. Okay, we'll put this value. So V out value is, we have now 6 multiplied by 0.4 divided by R value is 3 ohm multiplied by 1 lakh. Okay, and then multiplied by delta VC. Okay, or you can say ripple voltage. So here in this case, I think in the problem it has been given or not, I don't know. Okay, just let so change in the VC1 VC2 has been given as 0.1 1%, they have considered it. It is multiplied with 0.1, we can multiply it with. Okay, and that will be, we'll calculate now with help of calculator. So I will make bracket first, and that is 6 multiplied by 0.4, then divided by, it's like 3 ohm multiplied by 1 lakh multiplied by 0.1, and bracket complete. Calculate. So its value is 8 into 10 to the power minus 5. Okay. Its value is 8 into 10 to the power minus 5, or we can write C1 as 80 microfarad. C1 as 80 microfarad. Similarly, similarly, there is no change in the C2. Okay, so C2 value is again, it will be the same. Okay, because we need to change this value. Okay, so V0 B, and then R times Fs and delta Vc2. Delta Vc2. This value is also same. Okay, so 6 into 0.4 as it is 3 into 1 lakh 0.1, so it will be cost you around 80 microfarad. Now we have completed, you can say, design aspects of this. So we have got this value. I will again write the values. Okay, so what is the value of capacitors? Okay, so I will write first L1 value. Okay, I will L1 value, L1 value, uh, is 90 microfarad, 90 microfarad. Okay, that will be okay. And then L2 value is 90 microfarad. Sorry, microhenry. It's not farad. Sorry. So L1 is equals to L2 is equals to 90 microhenry. C1 is equals to C2 is equals to 80 microfarad. And then we have Vs is 9 volt. Okay, and yes, what are the other terms we have got? For PWM pulse we got 144, 144, this one 144. Okay, let us start, and now let us design. Okay, let us design this in the PSIM. Okay, so make a new file, and okay, I will show you this diagram first. Put values. Okay, so we got L1 equal to 90 microhenry. This is 80 microfarad. This is also 80 microfarad. This is 90 microhenry. This R value we got is 3 ohm. Okay, this is MOSFET. Okay, and then Vs that is 9 volt. Okay, this is what our diagram is there. Let us take this as a voltage source. Then I need an inductor. This is my inductor. Then I need a switch. I will use here. This is my switch, and for switch we need a PWM pulse, and then we require a capacitor here. Yes, and then again we need an inductor here. I will reload this. Then we need a diode, and one capacitor is required, and then resistance we require. Okay, now we'll make it connections. Okay, this is connected to this, is connected, this is again connected. Fine. Now we need a voltage probes. Two voltage probes I will use. I will give the names now. So this is my V in. Okay, I will display it. This is my V out. Display it. Okay, the value of Vs. Value of Vs is 9 volt. Then value of inductor 90 micro. Okay, so 90, and then you can put U, that means micro. Okay, and this is your L1. You can name it as L1 also. And this is what your C1, and the capacitor value C1 is 80 micro. So 80 micro. We have this L2, which is again 90 micro Henry. Capacitor value 80 micro. This is your C2, and then we have this resistance value, that is 3. This is your RL. Yes, and then we need simulate. Yes, we need to make sure that this PW, okay, frequency, always you can check the frequency. Okay, so by default it is showing 5,000. Okay, so it's 1,000, 10,000, 1 lakh frequency which is given in the problem, and then switching points you can make it as 144. Okay, 0 to 144 instead of 0 to 180. But I will skip this to display. That's also not required. Okay, we need a simulate control block, and keep it here, and yes, you can go for this 5 seconds. Okay, and then ground is required always. You can run the simulation by pressing F8, or you can click over here. Okay, so now it is running. We'll get the output curve, that is V out, that is 6 volt now in this case. Okay, it's running, it will take some time. Okay, maybe you can read here. The time I will give the name, Sepic converter design, and we'll change the color, and then font I will change 60. Okay, so I will keep it here. Let me make it as small. So we have the simulation. Okay, we have run this simulation. Okay, we'll calculate this. We'll see the measure V in. Okay, along with V in, if you want to measure other waveforms, you just click over here, add one screen, and in that screen you can take V out. Parallelly, you can see this is V in and this is V out. You can measure the output voltage. So this is what the measure tab is there. Okay, which will show you what is at the input, V in, what is at the output. You can measure. You can scroll down this value. You can measure all the values. So you can change. You can see that the values are changing over here. Okay, so input voltage is 9 volt, and then output voltage is 6 volt. Okay, output voltage is 6 volt. Is that clear? That's all for this 2 days. Okay, today's class. You can measure other quantities also. Measure other quantities also. Likewise, you can measure this current across this inductor. You can measure voltage across. Okay, okay. So that you can always measure. So that's all for today's class. So yes, I will stop now.